Hello everyone, welcome to today's session. My name is Wycliffe, and in today's video I want to share with you how you can obtain information on normalized difference vegetation index, a very important indicator of plant health or greenness of plants. So normally we have experimental plots in the field. For example, in tea fields, experimental plots are set up maybe to investigate the effects of a certain fertilizer on yield or a certain pesticide or something like that, herbicide, uh, on crop health or crop yield. But then normally people visit the field and obtain yield data, harvest the leaves, weigh them, and all these processes of laboratory analysis. But now I want to see how we can monitor these using satellite images without necessarily going to the field. Okay, so let's dive in. We will be using RGEE. We will be doing everything in R. So I start by loading a very nice library called RGEE. It connects the R people to Google Earth Engine. And then what is important is to initialize your uh, Google Earth Engine account. And then we can set drive is equal to true, or we can just initialize without setting the drive like that. Okay, so once that is done, we can proceed and load other libraries, because we will also draw field boundaries around our tea growing areas or our experimental plots. So I can say library map edit. This is a very important library because it helps us to draw boundaries of points, lines, and polygons, which we can then use to do the extraction. Another one we will use is dplyr. This we use to manipulate data or to wrangle data. And then we will use tidyr to clean some names. And lastly, we will use ggplot to visualize the trend of NDVI over time within our experimental plots. All right, so to start, we'll draw our plots. So I will call them plots. And then I say draw features. This draw features function is coming from map edit package. Okay, so I run that, and then it gives us this map background on which we can draw the location of our points, of our experimental plots. So let's, for example, say that you have experimental plots set up in this region, and you want to monitor them over time. So, for example, we can draw one plot here, and we call that is our plot, first plot, and then we have our second plot there. Maybe we have our second plot there. They normally they should be exactly the same size. So let's say those are your three plots: plot A, plot B, plot C, plot D, and you want to monitor them remotely without going to the field, right? So once we have created the plots, if you print plots, it's an SF object, simple feature collection, with some leaflet ID, and feature type is rectangle. All of them are polygons. So that's important for us. So what we can do is that first we can drop those other columns that we don't need. So we can say our plots is equal to the original plots, and then we use now the dplyr function to add plot labels or plot IDs. We can say plot ID, and then this plot ID, we give them the IDs like plot A, and then we have plot B, and then we have plot C, and lastly, plot D. The plots can be many. They can be more than these four, right? And then after doing that, you only select this plot ID, right? So our PLTs will therefore have only the plot ID. Is now also still a simple feature collection, but only has plot ID and the geometry attributes or columns, right? So we can convert these PLTs or plots to Earth engine object. So we do that by using PLTS, and then we pass it to SF as Earth engine object, right? So our PLTS is now Earth engine object, which is a feature collection, right? So to confirm that our plots are Earth engine objects, we can now we can visualize them. So we can say, first of all, we need to style them. So we can say styled so that they look, we don't have the fill and all that. For example, if I just say map $, add layer, and then we put PLTS EE, just like that, we will see that they are all gray. If we zoom into, I should have centered object, but no problem. If we zoom into our region of interest, we will see them as gray, dark gray plots. Okay, but we can style them. So we can style them by converting, first of all, to feature collection. So we say EE feature collection, and then we pass in our plots, PLTS EE, and then we use the style function. Okay, so inside the style function, we will need color. So we want the color to be the color of the borders of this line to be yellow. So in the hex color code, we start with hash, star or pound, hash or pound, and then we put 4 Fs and 2 zeros. So that gives us a yellow, or you could just type the word yellow. Then fill color, we want this to be transparent so that we can see the tea bushes or the tea in the background. Currently, it's a bit dark, so we want to see clearly. All right, so for that, we use 6 Fs, and then those are 1, 2, 3, 4, 5, 6, and then 0, 0. So that is transparent color according to hex color code. And then we want the thickness of the lines or width to be around 4 so that they are visible. All right, so once we do that, we can now plot our styled plots. We can map our styled plots. So map $. First of all, let us center our object now so that it's automatically zoomed on PLTS EE, and then we zoom it so that we can easily see the details at a level of 15. And then we can now add our styled layer, right? So add layer, and then we just put PLTS styled. All right. So that should, I didn't run the first one, okay, and then the second one. Now it should zoom it to our plots, and we can put the background. So we can clearly see T fields or T bushes inside our plot, our experimental plots, plot 1, plot 2, plot 3, plot 4, or plot A, B, C, D, right? So we are sure our plots are within where we want them. All right, so let's get our Sentinel data because that's where we want to calculate the NDVI from. Okay, so we want to look for the Sentinel image for the year 2024. So we start with January 2024, the first day, up to end date, which is January 2025. So this first date of January 2025 will not be included in the gathering of images. So it's exclusive. So we will only collect images up to 31st. The last date here will not be considered. Okay. So for us to use a Sentinel image, to use it to calculate NDVI, we know we must handle clouds. So we get the cloud scope plus or CS plus as CS plus, and then we look for the image collection data sets, and then within the data set, we look for cloud score harmonized, cloud score plus V1 version 1, Sentinel-2 harmonized, right? So that is a layer or an image collection which has the cloud probabilities, and we can use that to mask out cloudy pixels so that whatever median we will be using for the month will be clean image, right? Okay, then comes the Sentinel-2 image. So for the Sentinel-2 again, we do the same EE, but we know it's an image collection. So we go for image collection. Be careful here to type capital C and capital I. And then we look for dataset, and then why is it not showing collection? Okay, sorry, image collection, $sign, yeah, dataset, $sign, harmonized Sentinel-2 surface reflectance, this one. So if you want to see the all of it, it's this one. Okay, so after getting our Sentinel-2 image, then we can do the filtering so that because currently it is containing all Sentinel-2 images that have been collected since 2017 to date. So those are so many images covering Indonesia, covering USA, covering Angola, but we only want for a small field here. So we need to do some filtering, and we only need for this period of time. So we must filter both temporally, that is in terms of time, and spatially in terms of space. Okay, so we will create another S2 object, and we call it Sentinel-2. And for that Sentinel-2, we say filter bounds. So with filter bounds, we are going to filter only those that intersect with our plots, right? So we only want images for our plots. And then after that, we need to filter for the dates. So all other years, we don't care about in this example or in this demo. So we put our start date and then we put our end date because we had defined them up here. Okay, so after that, we are now careful about clouds. So we will link collection, and in linking collection, we link collection, which is the cloud score. And in CS Plus, we have a band called CS, another one is CDF. We are using CS for this demonstration. Okay, then we now loop through our images. So inside Sentinel-2, all the images that fall within our region of interest and within these dates, we go to those images and we apply a function. And this function will take each image. After taking an image, it picks the quality assessment band. The quality assessment band is obtained from image using the select function. When we apply select, we tell it to select the quality, the cloud score band. So once it has selected the cloud score band, we then update our image with that. So we update mask so that we look for areas where the quality assessment band value is greater than 0.6 and we keep them, right? Or we can set it as low as 0.5 for this demonstration. Okay, so I hope that ran without an error. It ran with an error. So the error, what does the error say? The error says unused argument end date filter bounds. Okay, so this is wrong. This one should be filter date. Filter bounds does not use filter date. Start date is not found. So start date is here, end date is here. Okay, then now it can run. Perfect. Okay, so our image here is now our image, which is almost cloud-free, which does not have too much cloud or is not too much cloudy. We have not used something like threshold for cloudy pixel percentage because that will throw away so many useful images. We just mask out cloudy pixels, right? Okay, then let us create a function which calculates for us NDVI. So we can say calc NDVI, we define a function, and in R that's very simple. We just pass an object or a variable or whatever it is to the function key or function, and then we say our NDVI will be from that image do normalized difference, right? So normalized difference between which bands? We know near infrared is band 8 and red is band 4, right? So those are the important bands. Those are the two useful bands for NDVI in Sentinel. Okay, once you've calculated the NDVI, rename it to NDVI, for example. Okay, so after that, we will be doing time series. We will be looking at monthly NDVI. So what we need to do here is to copy properties which contain time. So we say copy properties, right, from image. And the properties that we want to copy should be in as a list from the list of time system time start. System time underscore start, right? So that one contains the properties we need. Okay. So that function, therefore, we can easily map it over our images, right? So we can say S2 NDVI. Now this is NDVI with NDVI. We use our S2 and then we map the calc NDVI, right? So what we have here, if we can even print it, because we can just go on and on without seeing what we are doing. So we can print out this using ePrint and then S2 NDVI, just to confirm that we have no problem in the code. We give it some time to interpret all that information up there and pass it to Python API, which is a client API of Google Earth Engine, then work with the server to get the image, do the calculations, then bring it back to Python API, and then render it in R. So we have 74 images. We have 74 images for the NDVI for this year. As you may already know, Sentinel-2 image, it has a return period of 5 days or temporal resolution of 5 days. So in a year of 365 days, if we divide that by 5, then we get if we divide that by 5, we get 73. So 74 images is a clear indication that we kept all the images that were captured in that year. Even though some could have been cloudy, but we only masked the cloudy pixels. We did not throw the whole image away just because some parts had clouds. Only the parts that were cloudy were masked out. Okay. Because we want now data for months, or we want monthly data, then we need to create a list of that month. Yeah. So this becomes a list. We call a list of sequence from 1 to 12. And it is an Earth Engine list, not a normal sequence we have in R. For example, if you use a function like sec in R, you can easily see sequence of 1 up to 12. But when we are doing it in Google Earth Engine, then we need to provide EE list. Okay, then let us create monthly images. IMGs. So for the monthly images, we will take the months themselves and then we map a function. So we map a function, and this function we will use utility functions from Python. So we call utils and then py function, and then this py function will give it a function which takes every month, right? So once it has taken a month, let's say the first month, then that month is converted to Earth Engine number, right? So it's converted to what Earth Engine understands. And then the image becomes what we have in our NDVI, the 74 of them. For each of the 74 images we have, right? Filter. So we are going to filter. So filter date, filter, but then we use Earth Engine to filter this. So we use EE $filter $calendar range, right? So within the calendar, take from month to month, that is 1 to the end of that month by month. So if it is first month, move from month date, the first date of that month to the last date of that month, and using the month attribute. And then we get the median image for that period, right? Okay, so after that, we normally Google Earth Engine assigns some indices to the names. So we can provide better names by setting band names to the output or the median images we got here. So we can say, let's name them with a string. So Earth Engine string, which is NDVI. We want to name them as NDVI, but we also add, we add some text to it, which is the month itself. And that month needs to be formatted because it will come as a decimal, like 2.0, and that normally throws an error in Google Earth Engine. So we will call our image, and then we only pick the band we are interested in, which is the NDVI. Remember, it still has several other bands, and then we rename it, right? We rename it using the band name we have created up there. And then what do we set? We can set month if we want to, so that each image or each NDVI has got its corresponding month from individual M. All right, so that will give us our monthly images. Out of 74 images that it was not known which month which one falls into. They were just a series of images, but now we have made what we call monthly images. So from 74, now we have only 12 images, right? So we can get an image collection from this. So we can call it monthly image collection. And then because this one, we are mapping over a list. So what we have here is a list of images. So we can convert it to image collection by using Earth Engine. These are so many else. Earth Engine image collection, and then $ from images. Yeah, that is when we are creating an image collection from several images, which are in a list. So we create it from this. Okay. So we run that. Now what we have here as monthly IC is an image collection, right? So monthly IC is an image collection, and the size is 12. So if you check, for example, $size, I think it should be an Earth Engine number, and then you can get the information from that number, and then you see 12. So we have 12 images. Instead of 74 for the whole year, we've brought them down to the medians for each month. Okay, so this image collection, which has got 12, we need to convert it to bands so that we can do region or extract for regions. So we can call it monthly bands. And then for the monthly bands, we just use the monthly image collection, monthly IC, and then $to bands. So that it's not an image collection, but it's an image with several bands. So if you run that, you find that it's an image with 12 bands. All right, so if we want, we can clean the names, because names normally come with some indices. Monthly bands, let me print it. Monthly bands, then $band names, and then get info if you want to see them, the band names. So you see they have this prefix 0, 0, 1, 2, 3, 4 up to 11. So these prefixes, we don't want them. We only want NDVI for January, February, March up to December. I mean, it's not a serious matter, but we can decide to clean them so that we are working with clean bands. So we can say band names gets monthly bands. From the monthly bands, we get the band names, right? Like that. So that's band names of the image. But then we can clean names. We can make clean names, which is from the band names, which are not very clean. Then we map a function over them, which will clean their unwanted trailing or preceding indexes or indices, right? So we again rely on Python here, EE utils, but we are still within R, Python function, which takes a function, and then this function picks a name from the names. From the band names, it picks one name, and then once it has picked that one name, what do we do with it? We can pass it to a string, right? Pass that name to a string and then replace it with, now here we are going to use a regular expression. So for anything which is there, anything in that preceding number, which is between 0 and 9 or above. So we can use this beyond that, and then goes to an underscore, replace them, because there was these numbers and then underscore, replace them with nothing, right? So that will give us clean names. So if we check clean names, it's a list. And if we get info from them, we can see they are now clean names without these prefixes because we've replaced them with nothing at all. We've removed them. Simply speaking, we've removed them. So our monthly bands clean, this one now. We can paste it here and then say our monthly bands clean become monthly bands, and then we apply rename function. We rename them using clean names. Yeah, just like that, we now have monthly bands with clean names. Too much of cleaning the names, taking too much of our time. Let's get to the extraction. So to extract values for our sampling plots or for our experimental plots, we can use a reducer. So we can say maybe stat, let me just call it statistic. Then we use monthly clean bands, copy, paste it there, and then reduce regions because we have so many, several polygons to work with. So we call them our plots at engine, the 4 of them. And then the reducer we want to use is going to be EE $ reducer $ maybe mean. So we are looking for the mean NDVI inside this. And then after we get the reducer, we need to tell it at what scale. So natively, Sentinel image is at resolution of 10. So we use that. And then finally, we can then convert our stat to SF object. So we can call it maybe monthly SF. Very simple. We don't need to download anything. You don't need to think about Google Drive and all that. You just say Earth Engine as SF, and then you pass the stat. That should run without any problem. It's still taking a bit of time, but yeah, few seconds. We have our monthly stat as an SF object. Look at that. So simple features for four polygons, and each we have a value for each of our plot ID A, B, C, D. Okay, for each polygon. And then because it's an SF, we can convert it to a data frame. So we can say monthly DF gets the monthly SF, and then ST drop SF, ST drop geometry. So that comes from SF package. We can just say ST drop geometry, and we are dropping geometry from monthly SF from this. We don't need the geometry column from now downwards, right? Okay. So once we have our monthly DF, you can have a look at it. Monthly DF. They are now the NDVI values for each of the plot, and it is on a monthly basis from January until December. They are not in the right order, but we can rearrange that pretty fast, or when we will be visualizing it. Okay, so let us create a data set, or pivot it to longer format, because currently it is wide. But for a tidy data, it's preferable to have it as a long format so that we can easily visualize it. Okay, so I will simply call it data frame, and then we talk of monthly DF. Okay, and then we pivot it longer. So we can use pivot longer, and then in this pivot longer, the columns should be all those values that starts with, let's say NDVI, because we know they start with NDVI and underscore. And then after providing the columns, we need to tell it where the names are going. Let's say the names, we will take them to month, and then the values, we will take them to NDVI, right? After that, if you look at this, if we just run this up to here, you will have the plot ID, the month will have the what were the column names, and then we have now pivoted. NDVI values are now under NDVI. Okay, so after doing that, we may need to mutate to ensure that these months are separated so that we have month and we can plot accordingly. So we are going to apply mutate. So we use mutate function, which is coming from a dplyr package. And then our month, so we are just working within the same this month. So our month will be as integer, because currently if we just split it, it will be a character. So we can say as dot integer, and then we substitute. We don't want the NDVI, we just want the month. So we substitute everything which is NDVI plus underscore actually with nothing, right? And then this is obtained from the month column. So after doing that, we can arrange we can arrange them by plot ID and also by month. Okay. So if we just run this and check how it looks like, now it's clear. Now it looks nice that we can now see that, okay, it's now starting from plot A, this plot here, for month 1, 2, 3, 4, up to 10. Of course, there are more. It's just truncated at 10, but we have more. Monthly NDVI for this plot. All right. So after getting this, we can now pass it to our ggplot. We can now visualize it. So we can use ggplot, because let me just check the head of this so that we know what we are plotting. Head of DF. Sorry, I didn't run DF yet. Okay, like that, and then head of DF. Okay, so we can see what the variables we are dealing with. Okay, so ggplot function, and then we give it the data frame, which is the DF, and then for the aesthetics, we give it on the x-axis, we want the month to be on the x-axis, and on the y-axis, we want the NDVI values to appear on the y-axis. And then we want to color them so that we know which line refers to which plot. So we will color them by plot ID. After coloring with plot ID, we also group by plot ID so that we have a good legend. All right, so we can run that. We are passing this. We have not provided we've just set up the plotting area. We've not provided the plotting or the plotting parameters themselves. Okay. So we can add, for example, geometry line. We've not told it which vector or which way do we want to plot them. So we can say add geom line in which line width. For example, line width is maybe 1.2. That's normally a good line width to use. And then geom point, we want to add some points at each joint or at each month. So the size of those joint may be 2. We can adjust if it is not looking good. So we can also scale X continuous, and then we put breaks at between 1 and 12, right? Because we know there are 12 months in our data set. And then we can set our labels to be the month abbreviations. Because these are months. If you just run month abbreviation, you will see that they are Jan, Feb, March up to December. So those are the ones up to 12 we are having in our data set, right? Okay, so we can run that and we see our plot. So our plot has got the month and NDVI, and then we have the plot ID there. Maybe we give it better labels than that. So we just add labels, and in labels, you can set the title of the plot. Maybe we say monthly NDVI trend for experimental plots. Yeah, you have your plots, and then you want to see how they were healthy. How did my plots perform in terms of health last month? So the y-axis are the mean NDVI for the whole plot, and then color per month. So we first of all used the median for bringing the months together, and then we are now using mean to get the average per plot. Okay. Then we can use a different theme like theme minimal with a base of 14, base size of 14, so that the values are a bit clear. Okay, something is not right. Let's see what that could be. Object is missing with no NDVI trend, default size, monthly NDVI trend, title, experimental plots. Okay, so it's in experimental plots where we set title, not labels, it should be labs. Sorry for that, labs. Yeah, okay. So that is clear. Okay, so what do we see here? We see that the plants were very healthy. NDVI was almost 1 in January of 2024. February they were green, very green. They were healthy. March they were healthy. In April, plot A dropped a bit in terms of health, but the others were super healthy. But then when it comes to the month of July, something terrible happened to plot D, and then plot C, almost C and D, suffered between July and August, while other plots were performing well. Just for clarity, these are not true plots, so probably just coincidence that something happened in this plot or in this field. I can see there is some differences between these two plots, maybe different varieties of tea plant. this looks dark green and this looks light green. That's just a coincidence. But yeah, if you're looking at your plots and you can see something like this, it can help you explain the performance of the plots. Maybe yield from this plot D was lower in this month of July and August compared to yield from plot A and B. So with this, you can monitor the health of your plot. You can correlate these health or NDVI values with, for example, yield or leaf area or gas exchange or other agronomic attributes that you are measuring from your field. Not necessarily by going to the field, but using high resolution Sentinel-2 satellite images. You can calculate NDVI and you get them for each of your plots. The plots don't have to be close by here. One could be located in this T field, another one somewhere here, and another one elsewhere. But you can still monitor all of them comfortably within our studio. Okay, thank you so much for your attention. I hope you enjoyed this and you can use it in your experimental plots, whether you are doing it for beans or maize or sorghum or whichever crop, palm oil, cocoa, coffee, whatever you are studying or whatever you are interested in, you can monitor them. Or even forest, the health of forest or water body, whatever. Of course, not so much for water body when it comes to NDVI, but yeah, whatever variable or vegetation you are monitoring over time, you can check their health, and this can help you explain observed patterns in yield or biomass or something you are measuring from your experimental plots. Thank you so much for your attention. I will leave this script, the code to this, link to this code in the description of this video. You can get it from my GitHub repository. And as always, remember to cite all the sources of this information accordingly, especially the packages and the data sources for Sentinel and MapEdit and all those for your work. If you use it for academic purposes or research purposes, it's important to cite them. For example, in R, you just use citation, and then you get the citation, say, for MapEdit. So this is what you then use to, the BibTeX that you can use to refer to this package you used, or RG and so forth. So thank you so much, and enjoy coding.